future questions, or like what would be useful to do, what are the main like limitations, and how we can mitigate this limitation, I guess. But I can talk about the paper a little and what we worked on. So yeah, this first joint work with like great people. You may know some of them, I guess. And yeah, so what we investigate in this paper is just like mitigating generalization via Minimax regression training. So the TLDR, if you forget everything about this talk, it's just we do adversarial training to incentivize the agent to learn the correct reward function when there is some signal that we can amplify. So in general, we want to design AI systems that do what we want them to do. So usually, like in a row, we take a reward function and we think really hard about how to specify this reward function. We're like, great, if an agent optimizes this reward function, then it's gonna complete the task that we care about, and we're all happy, and we can go home. However, there are like some problems. Why? Because specifying this reward function is not necessarily easy. So the mental process of translating what we want the agent to do to like in a numerical scalar for like each thing that you can do is not straightforward. And there are like some failure modes. Like one failure mode is that we can have like reward hacking, which is the classic example, or the agent can like exploit the reward function that we define in some way to actually get a very high reward given our specification, but not completing the task that we care about. And also one other problem is that, well, maybe the agent just can't learn to do what we wanted. And this is not a reward function necessarily given by our failure mode in specifying it. So even if we specify the reward function correctly, well, there's like OOD things that can happen. The agent may like not be able to like just complete the task because there is a distribution shift or so. So we have these two main problems. But what we want, one other important failure mode that was like discussed in the literature, I guess, is that even if the reward specification is correct, so we have a reward function specified, the specification is correct. There is no exploit that the agent can do. And the policy is capable, so the policy is able to complete the task that we want to do. It's not that it's like the task is too difficult or the environment is like too hard or anything. These two things are in place. Even if these conditions hold, we still may have failure modes. And to see this, imagine training in these sorts of environments. So in mazes that looks like this. So the goal is getting this yellow circle. And all the environments look like this. And then you deploy your policy, and the environment you deploy looks like that. So it's like an OOD shift. So I guess people can guess what the problem could be.
It's allowed to go to the top left.
Exactly, yeah. So, well, we specify the reward function correctly. The policy is able to navigate the maze, but we just does something else. And intuition is that during training, there was not enough signal to distinguish between the reward function that we intended, going to the cheese, and the one that we did not intend, which was going to the corner. And yeah, I guess which agent will the goal pursue depends on the inductive biases of the network that you have. So depends, maybe learning a representation for the corner, it's easier than for the cheese, so you go there, or there are like many other work that people maybe in SLT have thoughts about. But what we want to do in this work is like being algorithm agnostic, in the sense of like we don't want to say, oh, if your inductive biases look like that, then you do well, otherwise not, or if like, you know, your algorithm has these properties. We don't want to talk about that. We want to like to give guarantees about how to solve this problem independently of the algorithm that you use. And yeah, so let's define again like what goal misgeneralization is, which I just said, I guess. So a policy which is optimal during training competently versus an unintended goal at test time. And this is like what we think is the best definition of goal misgeneralization, and I think very similar to what it was in the original paper of Laura. And this is the setting that we're working on. But as I said, if we don't have any signal towards the reward function, we don't know what the agent will do. So we study a slightly different setting in which we're able to give the guarantees and like leave this full ambiguous setting to like people that want to work on inductive biases of the network or other things. So the setting that we consider is called a proxy distinguishing distribution shift. And you can imagine that you can have two types of levels. One level is called non-distinguishing, and another type of level is called distinguishing. Why do we call them like that? Because this level does not distinguish between the true goal, which is going to the corner, which is, and the proxy goal, which is going to the corner. So this does not distinguish. While this level distinguishes the true goal. Why? Because you cannot be optimal with respect to both like goals if you have like some discounting, for example. So that level will like distinguish the true goal signal. And yes, the true goal and the proxy goal. And what was the setup that we have? In Langosco's paper, in Laura's paper, which was the original paper on goal misgeneralization, they say, oh well, if you only train these type of levels, then you fail. And then, okay, what if we, they have a plot which is like, oh, what if we show a little amount of these type of levels? Oh, the agent generalizes. But the proportion that they used was really large. And so we're like, is there like a middle ground? And so we train where, for some alpha, we have, with probability 1 minus alpha, we sample a level like, we show the agent a level like this. And with probability alpha, we show it a distinguishing level. And during training, alpha is small. And at deployment time, we sort of invert the distribution, maybe for some other parameter beta, but beta here will be large, and so we'll mostly show at deployment time distinguishing levels. So let's say, to be more concrete, 1 million levels during training look like this, non-distinguishing. 1 level is distinguishing. You learn your policy. Deployment time, the opposite. You have 1 million levels like this and 1 level like that. What's the performance of the agent? Is the setting clear? Yeah. So, okay. So what we show is that we want to like, okay, now analyze like what happens. And standard algorithms simply do one thing, maximize expected value. And so you have a training distribution, you find a policy that like approximately maximizes your expected value. And yeah, we use this notation where like V is like the return that you achieve and this lambda is like a level distribution, and this is like simply the expected return for each level, and that's like what classical like RL algorithms do. You just sample the environments at random from this distribution and see what happens.
So theta is not parameterizing a policy, but it's parameterizing a level.
Yes, that's correct. So theta is a level, and lambda is a distribution over levels that you may have.
Okay.
And that's the return. And then we have a policy. And well, of course, like in the case where like your policy, yes.
Can we return to the previous slide?
Yes, of course.
So why do you need to have a like non-distinguishing goal in the first stage?
Mm-hmm. Why do you need non-distinguishing?
Yeah.
I mean, we're just saying, let's suppose you train only in these levels. What happens is that your agent will fail because it cannot distinguish between the true and the proxy goal. So, of course, you need to do something with respect to this distribution. That's what we're going to do. But we're just saying, oh, goal misgeneralization can be induced if your training distribution also looks like this. Does it make sense?
I guess the point is, like, in this case, it's pretty obvious that like if you just move the cheese around, the agent will learn it. But like in real life, there might be like very subtle things like this, where, which you don't.
Correct. And the question is like, how do we automatically move this cheese around in a certain sense without like knowing beforehand what to do? That's a good question. So yeah, as I said, the policy is like approximately optimal, because if you consider a perfectly optimal policy, well then even seeing like one example out of a billion would like of non-distinguishing levels during training would be sufficient to like make you learn the true goal, even because it's like if you are able to like be completely perfect. But however, like RL algorithms are not perfect, so we're always like epsilon optimal with respect to some reward function. And so we call those.
What's arc epsilon max?
It's the policies that maximize these up to epsilon. We wanted like some clean notation to like do that, and I guess this was the.
So this is going to be like a large set of policies, right?
Depending on how large epsilon is.
Yeah, sure.
Yes. So yes, it's.
Okay, so the MEV policy selects from the set of args of epsilon optimal policies.
Correct. Yes. You train with MEV, and you know that one of the policies you obtain will be this, if you manage to optimize this objective.
Mm-hmm. Okay.
And what we show is that, well, it can, I guess, like maybe if you guys know why this may happen, it can be intuitive, but MEV suffers from goal misgeneralization. And the reason, and I mean, we have a theorem that says this, I guess, I state this informally, we can talk about the details. But the intuition is that if you have 1 million levels that are non-distinguishing and one level which is distinguishing, and you only care about being epsilon optimal, you don't need to solve that non-distinguishing level, because let's say like you only care about like epsilon suboptimality, but if the proportions levels that you see is smaller than epsilon, well then you can also like just completely ignore. And we see it like these just the theoretical results, then we see it also in practice. That's like actually what happens. But the intuition is that, in the sense of like, if the signal is not strong enough and you're only approximate or optimal with respect to maximum expected value, then you should not even care like about solving this if you only care about something in this set.
Yeah, as long as there's few enough. Yeah.
Exactly, as long as if you. Of course, if you're doing like half and half, your agent will then this will go. And yes, so that's of course very important. And yeah, of course, the point of the theorem is that there exists some policy optimal with respect to the MEV objective such that this happens. It's not for all of them because inside the set there will be also the true policies, but we don't have any guarantee that this happens. So that's why we say possibly suffers from misgeneralization. Is that clear? Questions? Okay. Instead, what we want to show is that, well, can we do something better? In the sense, if we're in this setting when there is some reward signal towards the true reward, can we do better than just like doing maximum expected value? And the answer is yes. The intuition is that you can think that this level that you don't solve, if you only look at this, it's like really, really bad that you don't follow the goal in that level. So regret is just like a measure of how far from the baseline you are. And if you take the minimax expected regret in this case, like I'm going to give more details, you basically care about solving all the levels up to some extent, like in the best ways possible. Like you don't want to be highly suboptimal, so to have like high regret in a very few levels, because your minimax policy will be like bad. And the minimax expected regret objective finds levels which like look like this. So you have a policy which wants to minimize this regret, so wants to minimize how far are you from the baseline. And this level designer, which is like, you can imagine it as being like someone that like decides which levels to show to your policy, wants to maximize the regret. So if we go back to the example where you start with like sampling 1 minus alpha distinguishing levels and like alpha non-distinguishing, if you completely ignore the non-distinguishing level, you have this other side that can decide to select some levels, and it's going to select the ones with high regret. But which are the levels with high regret? The ones that you didn't solve in the previous case. Yes.
Is it really strictly necessary to take the maximum over all possible probability simplexes over all levels? Can't you just pick the level in which the agent does the worst?
Mm-hmm. Yes, but then the agent, like you want this to like be an equilibrium of the game, of like these like two players or some game.
Okay,
and so it's like, yes, I mean, like you can do that, but then you know that your agent is going to like do something, and then you just like play the best possible distribution that you can, and then we have an equilibrium, and at this equilibrium, we show that this is an idea, but I guess we show that the agent is optimal.
Right. So when you train this in practice,
yes,
there's some mechanism that deliberately chooses the levels you're currently doing the worst on and like feeds you more of them or something like
correct,
that?
Yes. So,
okay,
yeah, that's exactly how we implement it in practice. So you can imagine this is the setting as like a recap. Maybe that was the information. So during training, that's usually what you see. You have like many non-distinguishing levels, and you have like one non-distinguishing, and you have like this failure mode. What regret does is like, in practice, how we implement this is that you sample some levels, the policy plays in these levels, and in the next stage, you have a designer that selects the levels in which the policy is the worst, and like show them again, or like plays, or like it can even decide to play new levels in a certain sense, and those will be informed by some regret estimates that it has over like your policy. And so the agent now will be incentivized to show you levels where you fail, and it does this automatically with this regret thing. And then we show that at equilibrium of like these two players zero sum game, when both players are playing the equilibrium, you are optimal in the sense of, and it's an if and an if. So your policy is epsilon optimal, and if you have an epsilon optimal policy, you can show that this belongs to like the set that is found by this. So it's like it's an if and an if. So it's basically saying, well, we're not solving the full ambiguous case, but we're only solving the one where you have like some reward signal to like incentivize the agent to like learn the true goal. But if you have this reward signal, minimax regret is the best thing that you can do. Of course, there's some problem, which is how do you estimate regret, because this can be hard, and we can like have some proposal in practice. And yeah, I guess this would be the main limitation. Of course, you have like convergence problems, maybe like I don't know, two-player games, or like sometimes like hard to optimize for. But these are two-player zero-sum games, so you have like these nice theoretical guarantees. Is this clear? Questions? I'm happy to repeat anything. Okay. Now we have some empirical results. So we have like, to recap, we have two theoretical results. And maximum expected value fails. MER does well. We explain the reason, intuition, we have the proofs. And we have also like bounds that depend of like if the designer is suboptimal, because if you go here, if you see in this statement theorem, we have like the agent playing an epsilon optimal policy and designer playing a max, but we also generalize this if this is like a delta max, and then your bound is like it's going to be like epsilon plus delta, so it's a linear dependence. But we have some results here. So as we remember, alpha is the proportion of distinguishing level that the initial distribution shows, and we can have like B0, which is the full ambiguous case, and then like I don't know, 1 in 100,000 and so on. And we want to see like how the agent performs. And here we train an agent with domain randomization, which simply samples from this distribution with these probabilities. And this is what the performance looks like. So, okay, the heat map shows that. Shows you first train the agent where the cheese in the corner with those probabilities. And then the heat map plots at deployment what happens when, with the mouse starting here, and for each square it plots the return that the mouse gets when the goal is positioned there. So if this like square is black, it means that when the goal is placed there at deployment, the agent doesn't solve it. And well, we can clearly see that the agent is going to the corner because it solves everything on the way, a little bit around, but it ignores the rest.
Right, so it only gets high return if it just happens to stumble into it along its path to the top left.
Correct. And this becomes slightly better if you see more examples, but even with 3 to minus 3, you're not really able to like get good results. And I mean, here is like 10% of the level. So like 10% is enough. But like if your proportion is smaller, the agent fails. And like Laura just tried like with 2%, the agent was doing well. So if the signal direct is a signal which is more enough, which incentivizes like PPO agents, like not loans. But what you do is then, well, okay, we plot like methods that implement this MER objective. And there are like two methods. I can briefly say what they do. PLR just selects, like randomly generates and selects a subset of environments to show. What Excel, after selecting the subset, also does like some edits in the sense of like maybe it takes a level with high regret and it changes the wall position somewhere and shows this level as well. And as we can see, well, the case where alpha is equal to 0, we see that the agent doesn't do much better. I mean, Excel does pretty well. Yeah.
So how can your MMER-based methods do any better, or like how can there be any difference in the performance of the methods with alpha 0? Because then there is no environment it can select and highlight, so you have nothing to boost, right?
Correct.
So why are the plots to the left different?
Yes, I guess it's because when you implement this in practice, you're still selecting levels with higher regret. And I think like what happens is that maybe you show levels which are a little bit different in like layout.
Yeah.
And so your agent is like, I don't know.
Exploring more.
Exactly, yeah. It's like more keen to explore or something.
Okay.
So it's just like it's better than choosing at random, choosing levels where your agent is like still not doing well because it's at the frontier of like the learnability.
Resolution between 10 to the power of -5 and 0, because it looks like Axel might be like working at like, I mean, Axel
between these two, you said?
Yeah, because Axel works at 10 to the power of -5, not at 0 obviously. Does it work at 10 to the power of -6, 10 to the power of 7, 8, 9, like, where does Axel break down kind of?
Yeah, I think we did like 1 to the -6 and it's still kind of working because these also like Excel with like the true regret estimate, and so we compute the true regret.
Okay.
Because you can also approximate it for like predictability reasons. So yeah, I think 1 to the -6 was still working, but then it's like we didn't include it because we didn't think that like one method would be informative. We wanted like to see a trend, and the trend like kind of starts from here for like many of the algorithms. So I think 1 to the minus 6 works, but yeah, I mean, I think there is like just a lot of stuff for like just like doing even like more experiments and whatever. It was just like a bit expensive to do because it's
like in principle, some of these methods should work as long as there is like 1 or 2 like as long as there is a couple of cases where the cheese is not in a coordinate data set, these methods should amplify them so that you get a good representation.
Yes.
And then it shouldn't matter how small the fraction is in principle, as long as
there's at least one. Yeah,
that's true.
And then because they should just boost them accordingly.
Yes. I mean, the theorem would work with like one environment in a certain sense, or like enough to train your agent. So I mean, I guess there are like some implementation reasons for like why it's not certain. But yes, the theorem holds for that, and we see that it does already like pretty well for low probabilities. So yeah, I guess definitely like one point would be like seeing how far you can go to the left. I think related to this, I mean, I can show it after.
So just some clues in the acceleration, the Excel case. You only take levels where the cheese is in the top left, and then you take the levels at which the agent does the worst on, and you perturb them and continue to train on them.
Yes, in the case of week 0.
Yes. So it never sees a level where the cheese is not in the corner, but you upweight, like you adversarially select the levels it does bad on.
Yes.
And this helps it generalize a bit, even though the cheese has never been anywhere else.
Yes, because in the case of 0, the perturbation is never on the cheese.
Yeah.
So you can, if the cheese is not there, you don't perturb the cheese.
Wait, this makes intuitive sense to me, because if you get a lot of reserve shit, you just get a lot of shit we have to explore a lot, so you just end up being more keen on exploring.
Yeah.
Okay, right. So you think the only reason it does better on this is because the mouse has an intrinsic desire to like wander around and explore, and just happens to bump into the cheese on the way.
Mm-hmm. Yeah, exactly.
Yeah, I don't think it's goal-directed behavior in a certain sense, because like here there is a hole, right? If it was like goal-directed, why would you get these and not that? So,
okay.
It's not competition. I'm not completely
So
sure.
they basically don't like optimize too hard for going to the top left corner because there's somebody trying to trick you all the time. And like, if you just try to do that, you often get tricked. So
Correct. And we have like other results. So these are like, I don't know what's so low resolution. But yeah, basically like we plot this alpha on the x-axis and the return is on the y-axis. And we have like, we plot the different methods. And this is like the return of the plot. So we see that at 0, they all do pretty bad. Then at 1e minus 5, MEV algorithms do well. So the red is Excel with like an oracle estimate of regret. So the true regret. A yellow is one like we estimate it with like some estimation.
and that's not better than PLR.
That's around the same as PLR with the oracle.
Okay.
I mean, it's better than I mean, here they're not the same because it's overlapping, but here is better.
Oh yes. Okay.
Oops, sorry. And yeah, so we see that like these methods also in practice do better. They're not perfect because if you don't have a good regret estimate or if your algorithms are not good enough, you won't like get perfect results. But basically what we're saying is like, well, these like the right direction in the sense of like you can work on like better regret estimates, for example, or like better algorithms for this, and these like should work because this red thing is kind of the theoretical ideal that like we implement like in an easy way, and so you see that these like almost perfect performance when you have even some small probability. I mean, it's not perfect, but yeah, I guess it's pretty good enough. So yeah.
So how fast do these train? Like, what's the penalty here? Because like, okay, so like, imagine that like your cheese is actually always just in the top left corner, okay? And you only care about having the cheese in the top left corner. But then, like, maybe to make sure if there are not being any subtleties that you haven't thought about that screw you over, you want to still run this like Excel with an oracle. And like, if you want to run that just to be sure, how large of a hit do you take in terms of like compute spending?
Yeah, so I think we train for the same number of environment steps, but of course, like you have this environment generation that or like selection that you need to do, or like perturbation. So I think generally it was like, I don't know, 10%, 20%.
Wait, so you train for the same number of steps, but I would presume that maybe the other thing converged faster or something?
Yes, but we have a plot on this.
So basically, how many training steps do you need before you converge?
So I think this plot answers the question.
Let's see.
So
Okay, what's the axis here? What are we seeing here?
yes, okay. So here on the single figure, alpha is this,
Yeah.
and this is like for how many environmental steps you use for training,
Okay.
and this is how the performance of the agent scales. And I mean, for Pilar and Excel, we didn't like scale this even more because the performance was already pretty good. But basically, you see that it's like for DR, if you train for longer, you become better. Like you have some improvement in this case. But mainly for like the high, like with a higher probability, right? In this case, the performance stays pretty similar even if you keep training for longer. So it's not only about training for longer, but even if you do it in this case, you don't see any improvement in performance because it's about the ratio. Well, and these algorithms like also start to improve and become better. Like I guess like between 100 million and 500 million, there is a difference. But as you see, these like the sort of like compute things that you do, and basically this shows that our algorithms like scale with like less compute and they converge faster in a certain sense. Because if you consider like Excel already with like I don't know 400 million time steps does better than DR with like even with like 3 times as much compute.
Okay.
So does it answer the question?
Yeah, also alpha equals 1, right?
Sorry?
Also alpha equals
Yeah.
1.
Yeah.
Yeah.
Because you don't.
No, wait, whoa. This, so what I'm asking is, assuming that you train on the cheese always in the corner, so this is alpha equals 0. No, here you're
Alpha is on the
evaluating,
x-axis.
but here you're evaluating on alpha equals 1, right?
Yes.
No, what I'm interested in is if you evaluate alpha equals 0 and train on alpha equals 0, how is the convergence of the different algorithms?
Okay.
You have this?
Yes, I think I.
Okay, nice.
So maybe somewhere in the appendix or the drinkers. Yeah, maybe. Yeah. So.
Because I would be surprised if there is no penalty to using this like access.
Yes.
There is no such thing as a free lunch, so there has to be like. Okay, maybe it's this.
Yes.
So here.
I mean, this is the
Okay,
proxy
but you
return.
can't really see it here, right? Because like you're always. I mean, if you look at the top, or I don't know which of these. Okay, what are different panels here?
Okay, so this is when you evaluate the algorithms with unambiguous levels.
And the different colors are just different training steps.
Are they not different algorithms?
Okay.
Excel,
Where are
PLR.
the training steps?
They're all the same. These are all 200 million.
Yes, as we saw.
So I can't infer training time from this.
Sorry?
I can't infer training time from this.
No, we don't have. We have this plot, the other plot. We don't have both at the same time.
Okay.
Yeah.
Okay. And you don't know from
Yeah. Okay. Yeah.
Because I would expect.
I think okay. So I think what you have is that you have, in theory, you have like some penalty because like you can't be like optimal at the same time. But I think in practice, the difference is like very low.
So I would guess that if you train with DR on alpha or on alpha equals 0, both when you evaluate and when you train, you should see that like
DR is
the
like
loss or the return gets like really good really fast, and then it's like basically stabilized, and you can train for longer, but it's just stable.
Yes.
Whereas I would guess that for XL or something, or one of these other ones, it would take more training steps before it starts to stabilize at the highest return.
Yeah.
Is this true, and do you know how much more?
No,
approximately.
No, I think I could give some intuition, but I think to be wrong. So I would like to say not sure. So I think it's like it takes a little lot. Like I don't think there was a big difference, but I'm not like take this with confidence.
Right.
I can run more expect.
Right.
Yeah, I don't want to say something which is not correct.
Okay.
Yeah, so we have this, and then to conclude, a correct root function and the capable policy may not be enough because we have Goldman generalization. Maximum expected value suffers from Goldman generalization, and this is like the behavior that you see in your agent. Minimax expected regret does better, theoretically and in practice. So yeah, you can also see sometimes in this GIF at some point Yeah, you see that the agent starts to go to the left and then it comes back. So it's like it's doing a bit more this exploration. So it's like epsilon optimal even in this case. And the future work that we will like gets more excited about. One is like having better regret estimates because as you see the results depend on how good the regret estimate is. And then is the case where alpha is equal to 0. So where you don't have this signal. Like can you get this signal somehow? How can you look at the models and see what it's learning? And I guess like many others. And the paper is like many other like results in the appendix, experiments, details, like extensions like partial observability and stuff.
Nice, thanks.
Of course.